Hello everyone, welcome back. This is lecture 2 of our journey toward developing a mathematical model of an amplifier using the BMR approach, bare minimum requirement. In today's lecture, we will discuss one of the deepest conceptual confusions in analog design, the active and passive paradox. We'll also connect this discussion with nonlinearity, power amplification, and the real origin of a small signal model. Let's begin. Okay. So here is the roadmap for today's lecture. First, we will revisit the major claims from lecture 1 and also correct some mistakes. Uh, then we'll discuss some comments and objections raised by engineers and researchers on LinkedIn. After that, we'll build the big picture intuition behind amplification. Then we'll discuss why we fundamentally want power amplification and the others thing. I will also show you the reference to the claim that I have made. Okay, the reference to the claim that we want P out is greater than P in, and the reference to the claim that there is nothing active. Okay, and I will also show you the classic definition of passive and active from Leon or Chua, and I will also show you the reference to that claim that the circuit theorems can't be applied to nonlinear circuit. Beside all of this, I will show you some hands-on proof that MOSFET is passive in biasing picture and total picture. Okay, but now you thought that you asked me a question, why we call MOSFET an active device, right? So I will show you the reason, also show you the reason that why we called MOSFET an active device. I will show you the real truth. And number 10, I will also have show you the hands-on proof that straight line doesn't mean always your linear. Okay, your voltage source, your current source, I'm talking about independent voltage source and current source is not linear. Okay, I'll prove that. Okay, then I will also show you some hands-on proof that LTI systems can't do power amplification even if there is a DC power source available. And after that, the summary of the lecture 1 and 2 from negative resistance to nonlinearity and discussion on future journey will happen. Okay, so we are going to slide 3. Okay, so let us first revisit the key claims from lecture 1. Our some key claims. The first claim was the minimum requirement of an amplifier is not voltage amplification. Okay. The BMR to be an amplifier, the quantity that should be amplified is not voltage or current, it's power. We want P out greater than P in, and that's the signal. P out signal is greater than P in signal. V out is greater than V in doesn't guarantee you an amplifier. Okay. Number 2, we need at least 2 port to model our amplifier. In 1 port, the input and output are not separate, and we need negative port resistant, and those devices are not fundamentally available for VLSI design. Okay, number 3, as we need P out is greater than P in, and law of conservation energy says no, you can't do it. So we need additional power source. Okay. Number 4, we fundamentally need non-linearity to transfer the energy from the additional power source VDD to signal source V in. Linear system fundamentally can't do this job. Uh, I'm talking about passive system. Okay, and every real system is passive, and so this linear system fundamentally can't do this job. Okay, now 5. 5. So the linear circuit theory can be applied to non-linear system where the paradox started. Okay, we are talking about linearity. We need linear non-linearity, but linear circuit theory can apply to non-linear system. The second thing is amplifier output should be linear with its input. No harmonics is expected, right? So here is the paradox. By using 4 to 6 point, I name that lecture the linearity and non-linearity paradox. Now, problem of lecture 1. Okay, I didn't clarify my target of this lecture series and background. So what is the target? The target is learning practical analog design from scratch that works in silicon, not ideal model of the book. Number 2, KCL and KVL don't hold for nonlinear system. This statement by me is completely wrong because KCL and KVL comes from law of conservation of charge and law of conservation of energy, which will be hold for any physical system. Number three, correction of number two. Basically, this was my vocabulary limitation. Sorry for that. I want to say that you can't use the circuit theorems, Norton's Thevenin superposition anymore. Okay, if your circuit is nonlinear, I will show you the reference. Okay, number four. I didn't show any reference, classics, books, or authority that claims this type of unusual things. Today, I will attach book snap and reference also. Okay. Number five, I didn't show any hands-on proof using basic theorem that linear system can't transfer power. I just showed Python code that proves visually. Today I will show you that. Okay. Number six, I didn't clarify the passivity theorem and also the definition of active and passive. Note that our target is to learn real world analog design, not for any exams. Okay. So the claim from LinkedIn comment, special thanks to him for this comment. It will make our lecture more insightful. The first comment was you confuse linear circuit theory with linearity of circuit. It actually means that linear circuit theory is not break with nonlinear circuit, and those two things are different. Okay, we'll see from some reference what was that. Okay, number two, amplification don't fundamentally requires nonlinearity. We need active device, and unfortunately they are nonlinears. It is right that we need active device, but in reality we don't have those. Okay, so we'll see from reference that and we'll prove that. Okay, number three, suggested experiment. Suppose there is a transistor with constant Gm across large signals and constant R as the load. This constant and ideally linear Gm times R product would represent an amplifier. Yes, it would represent an amplifier, but I am supposing there is nothing like this. Okay, this is ideal block. Okay, we are talking about real things. Okay, so we'll go to this point. Okay, hands on. Now the second LinkedIn comment, number one, we don't need nonlinear system to get signal amplification. Um, uh, we need nonlinear system. Okay, we don't need nonlinear system if there is active element and that is linear. Okay, and unfortunately all systems are passive. Okay, number two, nonlinear system create distortion. Why someone need desire for a nonlinear system if all they want is a linear amplification? That's a quite a beautiful quote. He is actually right. We don't desire for a nonlinear system. Okay, we want is linear amplification. So where is the paradox? We'll see that. Okay. Number three, in fact, there is no linear nonlinear paradox. Number four, if I have a system which can provide a constant gain between input and output ports, my goal of having amplifier is complete. Yes, he's actually right. This is a ideal model of an amplifier. But we are talking about real things that can fabricate. Okay, number five, if there exists a system which is linear and provide amplification means he's supposing this is active, then there is no requirement for nonlinear system. He's actually right. If you have a active element and this is linear, uh, you will have a power amplification. Okay, you don't need to transfer power from VDD to signal frequency. Okay, so if there exists, okay, so the thing is, if I can prove uh, there is nothing like active. Okay, every real element is dissipating power. Okay, and every element is passive, then this from this number point 5 we can tell there is a requirement for nonlinear system. Okay, let's see. So what is the big picture of lecture 1 and 2? The hidden story. We want to build, right? We want to build something that can amplify the energy. Okay, suppose I am talking in a microphone. Okay, so we want to build something that can amplify the energy present in my voice taken from the microphone. Okay, and it's giving to the loudspeaker. So this signal, this voice, this uh, energy present in this voice should be amplified. Nothing else. Okay. Now, the block is adding some power at the loudspeaker. Okay. Does that coming from the block? Does that coming from the block itself? If it's active, then yes, yes. Then we don't need any supply. Okay. If it's active, then yes. But is that coming? Does that coming from the block in reality? But it is not possible. In reality, it is not possible to create energy from nothing. Right? Law of conservation of energy and law of thermodynamics. That means fundamentally it's impossible to have circuit component that is totally active, no power dissipation. Okay, active circuit component is only an ideal theory. Even voltage source can drop some energy due to internal resistance. But in this lecture, we will count only ideal sources as active device. Okay, so our active device are the sources. Now, so it is clear that there is nothing inside that black box that can generate energy from nothing. That means it needs an additional power source. Note that ideal element don't need that. Our target is real, not ideal. But for system modeling, we need ideal things. That's okay. Okay. So finally, we can say the amplifier box itself does not generate any power. It's being driven by the microphone signal, which is very small. You know that. And the additional power source which can deliver as much power as it wants. Okay, right. So we can tell that from this point 1 to 6 discussed in previous slide, we can say that the block has to convert some of that battery power into the power that is going out into the loudspeaker at the signal frequency. This is the very important point, at the signal frequency, not any other frequency. I don't want my power at some other frequency. Okay, I want my voice to be amplified, not the noise, not the DC bias and the other thing. As long as you assume that this is passive and this is linear, you will not be able to get power gain from any LTI system. Okay, so there is no frequency conversion in LTI system. You have a signal at a certain frequency, the output will be only at certain frequency. There is no way that the DC battery can convert some of its power into the signal frequency. So we do have to go to some form of nonlinearity. Okay, nonlinearity is essential for power amplification. Even NLS nonlinear system are also passive. Okay, they also dissipate power and also heating up, but at least it's able to convert some of the battery power into the signal power. Now, the real meaning of power amplification. What is the real meaning of power amplification? The real meaning of power amplification here is increased signal power at some desired frequency, which can't be done with LTI. Passive, of course, there's nothing active, right? So, the question is, how does a real amplifier work? Or how to design a real one? First, we'll use the blessings of nonlinearity to transfer the VDD DC power to signal power. Number two, blessings always comes with a curse, and we already know those two curses. For this, we need a framework to linearize the non-linear element. Number three, then we can model the device as active with Taylor series by using local linearization. Okay. Number four, by the local linearization at a particular operating point, saturation or active, we can model it as a small signal model. Okay. And I want to say another thing, a small signal model is valid for all region, is no it is not valid only for active region. Okay, but we 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 want to draw, we want to get small signal model for active region. Okay, for its high GM property, and the other things also we'll see in next lecture. Now, in small signal model, our real world amplifier will look like a two-port amplifier system that can amplify power, and there is no additional source. So VDD will be invisible at small signal model as it has no incremental change. So now, finally our amplifier model is purely linear with the input and also have the ability to amplify the power of the signal. That's the thing. So now the reference to the claim that we want P out greater than P in. So the writer says here an amplifier increases the signal power, an important feature that distinguishes an amplifier from a transformer. Okay, So it amplifies the signal power. You can see here. On the other hand, an amplifier provides the load with power greater than the obtained from the signal source. Okay, let's see. Reference to the claim that there is nothing active. I will show you some other reference and also show you some definition of passive and active, and after that you will relate the whole thing. So not only from this only from this slide. Okay, let's see. Okay, the amplifier power supplies. Since the power delivered to the load is greater than the power drawn from the signal source, the question arises as to the source of this additional power. The writer itself asking question, what is the source of this additional power? The answer is founded by observing that amplifiers need DC power supplies for their operation. If amplifiers is already active, why it should need DC power supply? Active means generating energy. It will generate energy. Active circuit component. Okay, and passive, it will dissipate or absorb energy. Okay, nice. So this DC sources supply the extra power delivered to the load as well as any power that might be dissipated in the internal circuit of the amplifier. Such power is converted to heat. Okay, we have not explicitly found this DC sources. Nice. Okay, going next. Okay, so this is a book uh, of electric circuit, Nilsson Riedel 10th edition. In this book, we use circuit models that have already been developed. We do not discuss how component models are developed. And my goal of this course is to teach you how component models are developed. That thing, okay? That thing. So this is the ideal basic circuit element. That a basic circuit element does not exist as a realizable physical component. Okay. Uh, Next, ideal voltage source, ideal current source is a circuit element that maintains blah blah blah. These circuit elements do not exist as practical devices. They are idealized models of actual voltage and current source. Okay, going to the last line. We have sacrificed our ability to relate voltage and current in a practical source for the simplicity of using ideal sources in circuit analysis. Okay, so you can see more on Nilsson Riedel book. Going next, to see what is active and what is passive. Although we'll assume ideal elements, we'll try to indicate the shortcomings of these assumptions as we proceed with the discussion. Okay, there are some shortcomings. Okay, these elements which we will employ in constructing electric circuits will be broadly classified as being either active or passive. Okay, the distinction between these two classification depends essentially on one thing, only one thing, whether they supply or absorb energy. As the words themselves imply, an active element is capable of generating energy and a passive element cannot generate energy. Okay, clear? Okay, going forward. So this is a book from David Irwin. Uh, so it is important that we pause here. Okay, pause here to interject a comment concerning a shortcoming of the models. Okay, let's see. In general, mathematical models approximate actual physical systems only under a certain range of conditions. Rarely does a model accurately represent a physical system under every set of condition. Rarely does a model accurately represent a physical system under every set of condition. Okay, theoretically we could adjust the external circuit so that an infinite amount of current would flow, and therefore the voltage source would deliver an infinite amount of power. This is of course physically impossible. Okay, now hence the reader is cautioned to keep in mind that models have limitations. Models have limitations and thus are valid representations of physical systems only under certain conditions. Okay, let's go forward. Reference to the claim that there is nothing active. Finally, in our discussion of ideal sources, okay, we note that they are examples of active circuit elements. Ideal sources, active circuit elements. An active element is one that models a device capable of generating electric energy. Okay, generating electric energy. Passive elements model physical devices. that cannot generate electric energy. So when writer talking about passive element, he is talking physical devices, but here he is not talking about physical devices. Okay. So now reference to the claim again. So finally, it is important to note that our electrical networks satisfy the principle of conservation of energy. Okay, this is actually the law of conservation of energy from physics. Because of the relationship between energy and power, it can be implied that power is also conserved in electrical network. This result was formally stated in 1952 by BDH Telegen and is known as Telegen's theorem. So basically, this Telegen's theorem, which is stated in 1952, is comes from the law of conservation of energy. Okay, just think about your basic circuit course. When is your power is negative, it is delivered power, active device, power negative. When is your power is positive, I am talking about the passive sign convention, right? If power is positive, your element is absorbing power, passive. Okay, so negative means your power Vi less than 0. Negative means active. Your power Vi greater than 0. Positive means passive. Now, the sum intelligence theorem say the sum of the powers absorbed by all elements in an electrical network is 0. Power absorbed by all elements in an electrical network is 0. That means you can't get more power. Okay. So, now the classic definition of passive and active from Leono Chua. Now here's one thing. Here the writer sees and register a diode, a DC source, current source, PN junction diode, and all of these are registers. Okay, so writers make a statement here, and when we are talking about two port, we are talking about one port and registers. It doesn't means we are only talking about registers. Okay, we are talking about also sources. We are talking about also two port systems. Okay, let's see. So this is the book linear and non-linear circuit from this grandmaster. Okay, this is from 1987. So now let's read this. Thus the power delivered to a linear resistor is always non-negative, means positive. Okay, R is greater than or is equal to 0. We say that a linear resistor is passive if its resistance is non-negative, means positive. Thus a passive resistor always absorb energy from the remainder of the circuit. Okay, now the power delivered to a linear resistor is negative if R is less than 0. Negative. Okay, as current flows through it, the resistor delivers energy to the remainder of the circuit. Deliver energy, right? Therefore we call such a linear resistor with negative resistance is an active resistor. So we call such linear resistor with negative resistance is an active resistor. So here is the thing. We also see in lecture 1 we need negative port resistance to amplify, right? Negative port resistance. So this negative means active. So the whole story start from this negative resistance. Okay, then we are going forward and we are actually finding active element in nature, and unfortunately there are no active element. Okay, uh, now while linear passive resistors are familiar to everyone, linear active resistors are perhaps new to some readers. They are one of the basic circuit elements. Okay, nice. Going forward, here reader is telling that independent voltage source, your independent voltage source is a current controlled non-linear resistor. So he is also saying that your voltage is not linear. It's non-linear. Okay, I'll show you that. Now, there are some strict passivity consequences. A two-terminal resistor. Here, resistor means not resistor. It can be your current source or voltage source. Is said to be, or it can be a system. Okay, is said to be strictly passive if Vi is greater than 0 for all points. Vi on its characteristics except the origin 0 0. Why except the origin? Because at the origin your V and I both are 0. So the product will be 0. But here the writer set the constant V times I should be greater than 0, not 0. Greater than or equal to 0. It's greater than 0. Okay. So geometrically, this means that the VI curve of a strictly passive resistor must lie only in the first and third quadrant and stay clear of the V and I axis except the origin. Okay, now I want to ask you a question. Please revisit your ID versus VGS curve and ID versus VDS curve of MOSFET. Is it in second and fourth quadrant, or is it in first quadrant? It's in first quadrant, so it's clearly it's passive. Okay. Okay, now let's see. So our two-port resistor is said to be strictly passive if V1 I1 plus V2 I2 is greater than 0 for all V1 V2 I1 I2 satisfying the resistor characteristics except the origin. Okay, so from the whole discussion of passivity, we can say for a two-port system that the system will be strictly passive if the port 1 voltage and port 1 current, product of port 1 voltage and port 1 current, and product of port 2 voltage and port 2 current, and the sum of these two things is positive, means first and third quadrant. And if it's not passive, then it is active. V1 times I1 plus V2 times I2 is less than 0. Okay. Now, reference to the claim that circuit theorems can be applied to nonlinear circuit. So this is the book. This is not a circuit book. This is continuous and discrete signals and system from S. Soliman. So the writer says that when the system is linear, the superposition principle can be applied. This important fact is precisely the reason that the techniques of linear system analysis have been so well developed. Then the system is linear follows the principle of superposition. Now, what it means actually, if your system is linear, it will obey superposition, and to obey superposition, it have to obey two law of additivity, law of homogeneity. So these two laws simultaneously have to be obeyed to obey superposition, and then it will be linear. Okay, let's go to next slide. So this is a circuit book, Fundamentals of Electric Circuit, Alexander Sadiko, Chapter 4, Circuit Theorems. Okay. So the writer says that such theorems include Thevenin's and Norton theorems, since these theorems are applicable to linear circuits. These theorems are applicable to linear circuits. We first discussed the concept of circuit linearity. So the circuit linearity and linear circuits and the linear circuit theorems all are related. They are not different things. Okay. The property is a combination of both the homogeneity property and the additivity property. You can find more on this book. Okay. So now so let's start. Okay, hands-on analysis. Number one, we will see P out is less than P in concludes to the same passive definition from Chua. Okay. Number two, we will also see the passive definition for MOSFET in case 1, biasing picture, case 2, total picture, bias plus small signal, mainly quotient point and your incremental signal. Case 3, small signal picture. So in case 3, you will actually realize why we call MOSFET as a active device. Number 3, we'll see need for additional power source as the presence of active device in real violates the law of physics. Number 4, we'll see need for nonlinearity as linearity fundamentally can't have the ability to transfer the DC power to signal power. Number 5, I will show you a proof that your ideal voltage source and current source is not linear. Linear does not always means straight line. Okay. So we'll see all those 5 points outside of this presentation. Okay, let's go to our blackboard. Okay, so the number one, we are going for the number one. Okay, so this is number one. Okay, so let's think about a two-port system. This is like this. This is terminal number one, this is two, and this is the common terminal. Okay, now this is one terminal, this is one terminal, and this is the another terminal. Okay, so this is our common terminal. Now I will add a input source in the terminal. So here is a input source. This is nothing but V in, which is a function of T. This is my microphone, and this is the load. This is my loudspeaker. This is RL. Okay, nice. Now this is port voltage V1. This is port voltage V2. This is port current I1, and this is port current I2. Nice. Now, what is the input power? Let's draw a line to separate the port and the element. Okay. So, uh, input power means I have to look in from out. So, I have to look from this side into this side. So, this is P in. Output power means I have to look out from in. So I have here and I have to look here. This is P out. Nice. Okay. Now, so I'm telling that this is a passive network. I'm I'm assuming that it is passive, or I'm arguing that it is passive. If it's passive, if it's passive, then P out P out will be less than P in. Okay, nice. Now, what is P out? P out is the power that is transferred to the load. So this current is going inside. This is the port current. The current goes outside is negative I2. Okay, so P out is equal to V2 times negative I2, which is P in. P in is the power that is extracted from the source. Extracted by whom? By this system. Okay, extracted from that source by this thing. So this is uh, so this arrow is right. Okay, I1 times V1. Okay, nice. V1 times I1. Okay, so now we can move this one to this, and this is V1 I1 plus V2 I2, which is greater than 0. So we can say that V1 I1 plus V2 I2 is greater than 0. So that's the thing. So this is the definition, passivity from Chua. So this, if I tell you this is passive, it means V1 I1 plus V2 I2 will be greater than 0. If it's negative, then it is active. Okay, next. So now number 2. Number 2. So in number 2, why MOSFET passive? So why I'm telling you that the MOSFET is passive. Everyone know MOSFET is the active device, and all, we all know that, right? We all know that the MOSFET is the active device. So why I am telling you MOSFET is a passive? Because in reality every device is consuming power, every device is dissipating power, every device is passive. Okay, in reality. So why I'll break it down now. So number 2, why MOSFET passive in bias and total picture? Why MOSFET is passive in bias and total picture? Okay, so let's take the case 1. This is our case 1. So this is the case where we'll only bias the network. Okay, no small signal. We only bias the bias the MOSFET. Okay, uh, so we are supposing that it is two port, but amplifier amplifier is three port, not two port. Overall three port, input port. It has input port, it has power port, output port. Okay, input, output, and power. But ideally but in small signal model we can say amplifier is a two port LTI system. Okay, so why I'm telling this, because if I'm saying that it is a real amplifier, then here is input, okay, here is the output, and I have to give some power, okay, additional power from this port. So it is basically three port. So now I am I will I will uh, I'll ignore this power. Okay, only input and output port. Now let's see MOSFET as a two port device. So this is the common terminal. Okay, so this is our MOSFET, right? This is I1, this is I2. This current is going to that port. You can say why it is going to this direction. This is awkward, but you can see like this. Okay, the bias current. Okay, this IDSQ or IDQ. This quotient current is going from BDD to VSS. So it is going to that direction. Okay, like this. Okay, so this is not awkward. Now plus minus V1, this is plus minus V2. So what is I1 here? I1 is 0. What is V1 here? It is V1 is nothing but the VGS, get to source voltage. Okay. What is V2 here? V2 is VDS. Source is grounded. Nice. Or you can say source is not grounded. So let's say source is not grounded. It was more. It will be more general. Okay. Next, what is I2? I2 is nothing but IDS or IDSQ. Okay. Now, if I want to write that equation V1 I1 plus V2 I2, okay. What about this thing? This thing is 0. So I have to calculate this one. Okay. So what about V2? V2 is VDS. So what about this VDS? We have got this VDS from VDD. So VDS is less than VDD. That's true. We got from VDD. Okay, this VDS we got from VDD. So this is positive. Okay, this is a positive voltage across this terminal. Okay, to have it in saturation. VDS is greater than VGS minus V threshold. Blah blah blah. Okay, so this VDS is positive, and then we got some I2. Also, what is this I2? This is IDS going inside the MOSFET, and this is also positive. So this two term, the product of the two term will give you a positive value. So it will be always greater than 0. So it satisfies the passivity definition from Chua. Okay, nice. So what will happen? What will happen if we add a load here? What will happen? So basically, in ideally, there's no bias current flow through that load. If the bias current is divided and flow through the load, then the MOSFET will, that node particular node will be loaded, and the GM will be dropped. Okay, the quotient point will be changed, the operating point will be changed, everything, the environment of the MOSFET will be changed. So we don't want that our bias current go through the load. That's why I don't connect the load here. I have mimicked the ideal environment for biasing. Okay. So here we can, I mean, here we can easily see that this is ID and this is VDS, and they all are positive, and it's in first quadrant. So clearly it's passive. It's consuming energy, not delivering any kind of power. Okay. Okay. So now we are going to case 2. Let's see. Let's see case 2. Case 2. So what is case 2? Again, I1 is 0. Okay. I1 is 0. So I1 is 0. V1. So now this V1 is not V GS. It's small v capital GS, means small plus large is bias plus. So case 2 is bias plus small signal. Bias plus small signal means total picture. So this is the total picture of the MOSFET. Okay. Okay, this is the total mixture of MOSFET. The VGS, small v capital GS, which is VGS plus small v capital GS. Now V2, VDS, VDS plus small v capital DS. Okay, nice, everything nice. Now V1 I1 is equal to 0. So we have to calculate only the V2 I2. Okay, let's see. V2 I2. What is V2 here? V2 is nothing but VDS. Okay, VDS times IDS. So what is IDS? IDS is equal to IDSQ, the quotient current, operating current plus ID, the small signal current. This is nothing but GM Okay, now VDS times IDS. Okay, so what is this? This is nothing but VDS. VDS is VDS. This is actually VDSQ and this is VGSQ. Okay, so VDSQ plus a small VDS. Okay, then IDSQ plus ID. Okay, now here is a important things to notice, that is when your signal is going up here, your signal is going down here in the drain node. Okay, when your signal is going down here, your signal is going up here in this node. Okay, so 180-degree phase shift, right? Now, so for positive half cycle, positive half cycle. So for positive half cycle, VDS, this thing is negative and ID is positive, right? GMVGS. Okay, now uh, for negative half cycle, VDS is positive and ID is negative. So what I want to tell that if this is V1, okay, and this is your bias at the gate, we are talking about this VGSQ, and this is your small signal. Okay, nice. So this is the thing. This is the small VGS. Now we are talking about VDS. Okay, So this is VDS, this is V2. Okay, this is time, this is time. Now let's see carefully again. Now this is your VDSQ, and this is your amplified phase shifted signal, but the overall range, you can see that it is impossible that this thing will be amplified such that the whole value will be negative. This value is also positive because the MOSFET has to get that type of GM in saturation, and it has to maintain a headroom, a voltage margin that is greater than VD set, okay, the saturation voltage. So the MOSFET have to keep in saturation. So this voltage will always be positive, okay, how regardless of the swing of the this node. That means this, where in positive half cycle VDS is negative, okay, nice, there is a chance that these two things the two product will result as a negative thing, but this VDS is negative, but this is small from this VDSQ. So this VDSQ is large and this is small, and a small thing is subtracted from a large thing, so this will be a positive value. And when it is positive IDSQ, what about IDSQ? This is IDSQ. This is your IDSQ, okay? And this is nothing but your GM VGS. So when this is negative, this is already positive. So this is already positive, this is already positive, this whole thing is positive, and this is also positive. So positive times positive also positive. So if you go for the negative thing, this VDS is positive. Okay, so this is positive. Now, what about this thing? ID, ID can't go to negative or can't cross this zero axis. If it cross, then the MOSFET is off. It is in cutoff region. So our target is to keep the environment ideal for the MOSFET to act as an ideally controlled current sources, voltage control current source, right? VCCS. So in case 2, we can say that V1 I1 plus V2 I2 is greater than 0. Means in total picture, MOSFET is a passive device. Okay, let's move forward. Now, now the real question appears. Everyone will question me, and someone will also comment me in LinkedIn. Why then why we call MOSFET as a active device? Why? So let's see. Let's see case 3. Case 3. Uh, so we are talking about the small signal model. So now I am drawing the two port again. Here is my controlled current source, which is GMVGS, or I can say it's GM1 1 prime for port 1, which is V1 1 prime, V1 1 prime, which is nothing but VGS. Okay, nice. So I'm not making complicating this. This is VGS, no 1 1 prime, just forget this thing. This is GMVGS, okay? And this is your plus minus VDS or V2 2 prime. Okay, this is VDS, no 2 2 prime, VDS. So we are not talking about this thing, we're talking about that one. Okay, so let's suppose uh, so uh, let's suppose we we are connecting a load now. This is RL. Okay. So this particular current is going through that direction. When it is going through this direction, it is showing that negative sign. So from passive convention, we can say that this I2 is negative. Okay, so that's why our VD is a 180-degree phase shift. You also saying that here in this particular contraption, we can see that it is acting like a linear resistor, right? Acting like a linear resistor that has negative resistance. Okay, that's the thing that make it active. Okay, the negative resistance. Okay, now in a small signal model, for this I can say I2 times V2. So what is this I2 from this side? This is nothing but GM times VGS, but there is a negative sign. So negative GM times VGS times this V2. This V2 is nothing but VDS. Sorry for that, it is small d, VDS. So from this thing, this is negative, this is positive, and negative times positive is actually negative. So we can surely say that as I1 V1 is 0, we can say that I1 V1 plus I2 V2 is less than 0. So it is active. So now MOSFET is a active device. So basically MOSFET was not active device. We are forcefully make it active device. It's our work. It's analog designers work to fight with those non-linearity and make that thing active. Okay, so MOSFET is a incrementally active device for small signal model. Okay, and we want to make a small signal model for active region, right? For those saturation region, those flat band ID versus VGS. Okay, this thing ID versus VDS, we want to bias our MOSFET in this region, but that doesn't mean that a small signal model is valid only for this region. Small signal model is valid for all region. This is incremental model. Okay, so in next lecture I will also uh, clear this type of concept, that a small signal model is valid for all region and all the other things also. Okay, now uh, the most important thing, number 4. Okay, number 4, LTI system can't do power amplification. Okay, so going to number 4, LTI system can't do power amplification even if there is a, I am talking about real LTI system, the passive one, not the ideal one. Okay, even if there is a additional, for ideal LTI system which is active, it it don't have necessity to transfer power from DC to uh, some power. Okay, so if there is a additional DC power source, so let's see this is number 2. Okay, so we should go to number 3 first, but I write somehow 4. Okay, let's see 4. Then we'll see the number 3. Okay, so LTI system can't do power amplification. Okay, let's see the number 3 first. Okay, then we'll see 4. So number 3 first. Okay, so what is number 3? Number three, I don't remember that. What was number three? Let's see in here. Number three is we'll see need for additional power source as the presence of active device in real violates the law of physics. Okay, so we have to see the need first. Number three, we have to see number three first. Okay, number three. Okay, let's let's assume let's assume we have active device. Assume, just assume we have active device in reality. Okay, let's assume we have active device in reality and also linear. Okay, nice. And also linear. Like the comment, okay? I think you remember the LinkedIn comment section. Okay, let's assume we have active device in reality and that's also linear. Okay, so uh, I'm drawing that device. This is nothing but a voltage control voltage source. It is something like this. AV V in, okay, and this is V out minus V out, and this is some V in. So let's this is the V in, okay, V in of T, and I'm removing that thing. This V1, okay, nice. Now, now the question, where is the load? This is the load, okay, nice. This is the load. So now I'm drawing a border. This is a border. This is a border. This is the system, and this is the environment. Okay, system, environment, border, environment. So this is acting as input to the system. Okay, this is acting as the input of the system. This is not the part of the system. This is not the part of the system. This is the load of the system. Okay, this is loading this one. Okay, now and as this is ideal, this is not loading. Now from here to here, we'll see P in. Okay, from outside to inside, this is input. From input to from inside to outside, we'll see the power delivered P out. Okay, nice. Now what is V in here? V in is V in times T is nothing but Vp sine omega t. So what is P out? So P out is nothing but AV square Vp square by twice RL. It is nothing but the average power formula, the Vm square by 2RL, or the Vp square by 2RL. So the V out actually here is nothing but AV times V in. This is a voltage amplifier, right? Voltage control voltage source. Now the thing is, what is P in? Can you comment on this? What is P in? This what about this current? There is nothing inside. Okay, no connection here, nothing inside. So this pin is zero. So is it possible? Is it possible to generate energy from nothing? Your pin is zero, but your P out is some number. Okay, so let's see the efficiency. Let's see the efficiency. What about the efficiency? The efficiency is eta, and when your limit P in tends to 0, this eta, this whole thing will tend to infinite. How? Because eta is nothing but P out, the signal power, divided by P in. Now this limit P in tends to 0 will make this whole expression tends to infinite. This is quite impossible. We can't make equal sign to infinite. It is a concept. Infinite is not a number. Now the question is, is it possible to generate energy from nothing? Free energy? Free energy is possible? No. There's nothing free in this real world. you have to pay a price. Okay, you have to pay a price. So is it violate the law? Yes. Okay, but it's beautiful, it's beautiful in your simulator, in my simulator, in a Cadence Virtuoso or other simulator, it's beautiful to model. Okay, it's beautiful to model from system level. It's our ideal wish, it's our ideal goal to make this, but it's not the actual real model. We want to make it from scratch, and the real one, not this ideal one. Okay, I think everyone is clear now. Number 4, LTI system can't do power amplification even if there is a additional DC power source. Let's see this point. Okay, suppose I have a LTI system. This is my LTI, linear time invariant, and this is passive. Okay, so this is the VDD, which will act as a source, and this is our sink, which is VSS. Okay, this is the terminal. This is another terminal. Now we'll connect our source. This is source resistance. This is our V in, and this is RL. Okay, so this is linear. Okay, so it will obey the superposition law. So in superposition we generally activate one source and deactivate the other, activate only one source at a time. Okay, so number one, only V in T is present. Okay, and I am deactivating VDD. So deactivating VDD. Okay, so I am deactivating VDD. Now what's happened? We can see by deactivating VDD, it will look like this. This box, this thing is grounded. I have only RS and this V in T. Okay, and this is your RL. Now, can you comment about this V out? What is this V out? Okay, this I already say this is a passive network, so there will be dissipate some power here. Suppose I this V out is some this is some A times VP sine omega naught t. Now, can you comment on this A? Can you comment? This A should be less than 1. Why? Because this is passive network. It will um, there will be some drop of voltage. Okay. So this A is less than 1 now. So because all real element is dissipate power. Okay. Now I think you all realize this thing. So what about the power? Okay. Let's see. Let's see the next page. This is T. This is VNT. This was VP. Okay. And I also tell that it is linear time invariant and it will not be shifted. Okay, so this point will be fixed, no delay. Okay, and this is VP, this is will be alpha VP, this voltage will be alpha times VP. Okay, alpha VP, alpha is less than 1 here. Now what about P out? So what is the P out here? This is V out T, this is V in T, this is V out T. So what is P out? P out is nothing but alpha square Vp square times twice RL, which is less than or equal to P in. Okay, because alpha is less than 1 is a passive thing. Now case 2. So this is case 1. Now case 2. We are deactivating. We will deactivating this V in T. Okay. will deactivating this thing. This will be deactivate and this will be activated. Okay, so now let's see. This is so now this is number 2, deactivate signal source. So we are deactivating the signal source. So it is grounded. Nice. This is LTI again. This is passive. Everything is nice. This is VDD and this is our RL. This is also nice. Now, what is this V out T? This V out T is written when V in T is 0, means deactivated. Okay, this is nothing but uh, some B times VDD, B times VDD. Okay, can you comment on this B? What is this B? This B should be less than 1, right? So now we can say that uh, uh, V out T is nothing but this one. This is B times VDD. So V out T, so the total, so now the total from superposition theorem we can say V out T, the total one is V out T when your VDD is deactivated. VDD is equal to 0. Okay, right? Plus V out T when your V in, the signal is deactivated. So what is this? This is actually nothing but this one. This is actually this thing. B VDD and your signal, the same signal, which is A times VP. Now, if I want to calculate the power of the signal, the thing is the signal is shifted upward, but we want something like this, more amplitude, not shifting. So the actual signal power is same, alpha square VP square 2 times RL. We want amplified version, but this is shifted version. So the conclusion is no DC power translate to signal power. And the conclusion is a linear time invariant network can't do power amplification even if there is a DC power source available. Okay, let's go forward. So what about our last thing? Well, what was the last thing I forgot? Let's see. Okay, I'll see the proof that your ideal voltage source and current source is not linear. Linear does not always means straight line. I prove all those 4 things. Okay, okay. Let's see the number five. Let's see the number 5. Okay, just recall about your voltage source or current source. Okay, let's see it with a voltage source. Suppose this is your voltage source, plus minus V. Okay, and you can get a current from this voltage source. Okay, let's see. Let's assume that this V is 2 volt. This V is 2 volt. So what is V here? V is equal to 2. What type of equation is this? This is something like y is equal to some constant or x is equal to some constant. A straight line. This is a parallel line of to the x-axis or parallel to the y-axis. It depends on the curve I versus v or v versus I. Let's see I v curve. Okay, for this. So ideal voltage source will give any voltage regardless of the current. Okay, so 2. So think this is 1, this is 2. Okay, let's see. So this is 2. Okay, let's make it more beautiful. Let's make it more beautiful with this thing. Okay, that's nice. Nice, nice. Okay. So this is the curve. Now the question. Uh, so we'll test this system is linear or not. Okay. I'm talking about this straight line or your y is equal to mx plus c. Okay. You can say y is equal to mx plus c is linear. Yes, this is linear in the sense of mathematics, but this is not linear in the sense of linear system. We are talking about linear system. Okay, to make it linear, it have to go through the origin. Okay, and this is also not linear. Now I will show you the proof. Uh, to make it linear, it have to obey the superposition, and to obey the superposition, you have to it have to it have to obey two law of additivity and law of homogeneity simultaneously. If any of them break, it will break. It will not linear. Okay, let's see. Suppose I have a system, and this system is nothing but this voltage source. Okay, and I have input of x of t and output of y of t. Okay, that's nice. So for homogeneity property, if I scale this y of t by a scalar, suppose the scalar is 3, then this will be 3 y of t, right? Now if I scale this x of t with the same scalar, then this will be 3 times x of t. Okay, now if I give this input to the same system, this is system, this is actually the voltage source. Okay, this is actually the voltage source. If I input the same system and the output is same to this is linear. This implies this obey the law of homogeneity. Okay, but now I want to say that this voltage source. Okay, let's see, from this v is equal to 2 volt. Okay, so uh, let's see, this is the output. Okay, which is equal to 2 volt. So now this 2 volt, so you can also write like this vi. Okay, now this is 2 volt, so this 2 is going to 6 if I scale the output. Now if I scale the input x of t, I don't know what x of t was here, right? Suppose the x of t was previously 1 ampere. Suppose this is 1 ampere. Now this 1 ampere will multiply with 3 and will give 3 ampere. Now this 3 ampere, this voltage source, it wants 6 volt, but it will not get 6 volt, right? In 1 ampere, it will give 2 volt. In 2 ampere, 3 ampere, 4 ampere. In for all current, for any current, it will give only and only 2 volt. It is fixed. That means the system output is not following the input linearly. So that means your linear lines doesn't means your source is linear. Okay. So what is the thumb rule? For linear system, you have to check that the things going through the origin or not. Okay. If the straight line going through the origin, it's linear. Otherwise not. This is also not linear. Y is equal to mx plus c. Okay. So that was a huge discussion. Uh, it is too much late night. Okay. Now let's see after this hands-on analysis. So the summary of lecture 1 and 2. So now the summary. We wish to make a mathematical model of an amplifier by using BMR approach. Okay, where by BMR I mean bare minimum requirement, the fundamental requirement. Next, then I asked question about the quantity that should be amplified because most of the learners believe that V out is greater than V in is the BMR and the quantity is voltage. And now you already know that P out is greater than P in is the BMR. So the quantity that should be amplified is the power of the small signal. Then we start to find active device and want to amplify with a one port resistance. We found that the port resistance should be negative to call it as a active device, right? So from here the journey begins. Okay, the port resistance should be negative to call it as a active device. Okay, remember that thing. We also find out that to be active, V times I should be less than 0, means it will be in second and fourth quadrant, but our real device lies under first and third quadrant. That means every real circuit device is passive. They all only dissipate power. You have to understand this thing very clearly. Okay, every element that we have in real is passive because all of them only dissipating power. The only thing that generates powers are the batteries, and inside our IC we don't have them. Okay, now then we found out the reality that active circuit element is a theoretical concept that used only for ideal sources, dependent and independent sources. Okay, then there's nothing active in reality. Okay, every element dissipates power, and using basic common sense we can also realize it that it is impossible to create energy from nothing, absolutely from nothing. Okay, we also we saw that thing, and we conclude that we need additional power source to amplify the input small signal. Then we try to transfer the power from zero frequency to omega frequency, right? The VDD is in zero frequency, the DC power source frequency with the LTI system, right? And we successfully failed. Here we successfully failed with an LTI system, passive LTI. So we realized that the fundamentally we need some form of non-linearity to have the ability to transfer the power as linear system. Fail to do so. We don't have option. Okay, remember that. Then we also realize that our ability to do circuit analysis got reduced, and also we got harmonics problems at the output. We want linear relationship between input and output. We also got the linearity and non-linearity paradox. Also we got active and passive paradox. Now at this moment, if you I'm talking with you, if you don't see my lecture 1, I think this lecture 2 will some create some difficulty for you. Okay, so you have to see the lecture 1 first. So now, so we also got the linearity and nonlinearity paradox, and also we got the active and passive paradox. For solving the active and passive paradox, we can recall the case 1, 2, and 3. And we can recall the case 3, then we will saw that why we are telling MOSFET as, as an active device. Okay, hand-on analysis. Basically, our amplifier is 3 port, input, output, and power port. But the amplifier active device definition is for 2 port. And we that's the real definition. Okay, check the sedra Smith book. So basically in small signal model VDD is gone when VDD is gone, vanished, and then we see it as a active device which is two port. So there is the active passive paradox which paradox solved. Basically what happens, you forcefully make it active. You do some DC bias, you get some additional power source, and do some tuning and a lot of things. After that, you can visualize these as a small signal model in active region. And when you draw your as a small signal model, when you draw, this is an incremental model. So your VDD is not incrementally changing. So VDD is gone, right? This your power is gone, and you are seeing that in your you see, you are seeing that there is no VDD. The VDD is gone, vanished. So you see that that the device itself generate power. Amazing, amazing. This is an active device, but you have to remember there is a VDD. There was an additional power source. Okay. Now, finally, our target is to develop circuit such that it satisfies the target small signal model. Now, discussion on future journey. Okay, here is the four amplifier type models. Our main target of this course is to realize those four ideal amplifier type with MOSFET from scratch that can pass in real silicon. Okay, not in just a exam. We already developed the idea of simplification and related paradox, active and passive solved. We will transfer the power VDD into the VNT by using the beauty of nonlinearity. And after that, we will set some mathematical constraints on the input signal and suppress the nonlinear effect, harmonics by the local linearization. Okay, so congratulations. Now we have a real active device and it is linear. The paradox is solved. So thank you. See you soon.